Solving quadratic models. A quadratic model is an equation in two variables that describes the relationship between two quantities for an authentic situation. That's a rough idea, rough example. Remember, quadratic models or quadratic equations are in the form of y equals ax squared plus bx plus c. You may not always have the y under, but for reference. Let's say in this case, we have h equals negative 2t squared plus 6t. Our c value in this case is 0. So we don't necessarily have to have this 0 there, agreed? And let's say this represents the path of a ball traveling in the air. Well, I guess it's kind of hard to see it, right? So let's graph it. There's a quick sketch if you graph this. You're welcome to graph on a calculator and verify it looks something similar to that. This is a large image though. And let's say there's a ball there. There's the ball. Can you see the ball at the beginning before it starts traveling in this case? And we have a, well, stick figure player running to kick our ball. There he goes. And he kicks the ball. And look at the ball travel. It's traveling in slow motion. Now we can see a little bit more easily. So it travels through our parabola. And there it is. It's reached the peak, right? Our vertex. The peak of our parabola in this case. And watch the ball continue to move. In this case, it's now start to fall. And then it lands on the ground there again. Does that kind of give you a visual of how we can use parabolas or quadratic models? So keep in mind we have a line of symmetry, and for this case let's approximate our vertex, the highest or lowest point. In this case it's the highest point that the ball reached. So roughly we can approximate it to be, I would say 1.5 in the x and 4.5 in the y, or the height in this case. So let's say it represents 1.5 meters and 4.5 meters high. So if somebody kicked it forward 1.5 meters and 4.5 meters height to reach the maximum. Okay, so once again, we call that our line of symmetry is at x equals 1.5, agreed? And we can tell that the y-intercept, or our h-intercept, representative of the y, starts at 0, right? Times 0, that's the t representative. And the t-intercepts, well, y values are 0 for both t-intercepts, agreed? We have two of them in this case. So the y-intercept, we can tell it starts at 0, 0, 0. Height of 0, time of 0. And initially, when the player kicks the ball, it starts at height 0. So the timer, t-intercepts, would be 0, 0 as well for this particular case. So both the y-intercept and the t-intercept match at one particular point. But the secondary point for t-intercept is when it's on the ground again. And that would be at 3 meters. Okay, pardon me, 3 seconds. Even though it was in slow motion. So at 3 seconds, it's a height of 0 meters. And hence we kind of introduce the idea or the concept of quadratic models through graphing. Once again, keep in mind, visualize this like a ball traveling in the air if it helps you.